So thank you all for attending this next edition of the SIAM SAGA. If you're new to SIAM SAGA, you can put questions in the Q&A. And then if me, Kathleen, or somebody else might read them out to, or another co-host might read them out to Sonja, or we'll save it to the very end, and you might be asked to unmute yourself at the end of the talk. And so yeah, so with that question information, we'll get started. And I'm very happy to introduce Sonja to give us a talk on randomness in commutative algebra, in particular random monomial ideals. Okay, so Sonja, take it away.
Hi, thanks for having me. And it's actually, oh, okay. It's good to be here. I am thrilled to be, the one who gets to say, hey, Happy New Year in the craziest New Year ever so far. Hopefully we'll get back to normal very soon. I wanted to tell a story of actually it's a set of different projects. Some are a few years old, but sort of the work is ongoing. And I found it surprising that I haven't talked about this before, even though it's from several years ago. So I want to tell you ask you a question. So suppose you have a set of ideals. So you have an ideal, I don't know, pick your favorite polynomial ring in n variables, okay? And you have an ideal, I don't know, f1 up to fs, and you have another ideal, G1 up to GS, and you keep writing ideals because maybe you have some kind of an application, and you're wondering, wait, I'm just, looking at examples and searching for a property. Maybe your property is whether this coordinate ring is arithmetically Cohen Macaulay. Maybe you're wondering whether the ideal is monomial and you create the corresponding level algebra or something like this, and does it have something called the weak Lefschetz property? Maybe you're wondering what is the regularity of all of these ideals. Maybe you're wondering whether you're looking at the wrong set of examples and trying to find, on average what happens. And so you're looking at the large family of ideals. Maybe the computations are too expensive. And so you would like to quantify, okay, I made this example randomly from this application and I saw what I expected to see, versus I don't think this property actually happens often. So let me try to create an extreme example by using probability. And so this work is guided by questions like this. How can I, in a given family of ideals, how can you figure out whether a given property is generic in some sense or extreme in some sense, okay? Where the word generic is in quotes, because if you're a formal commutative algebraist, it has a certain meaning. If you're a statistician, it has a different meaning. If you're an algebraic geometer. So what does genericity mean in whatever set of examples you're looking at and whatever property you're looking at? So how do we explain what this means? Okay, so from a point of view of randomness and statistics, this has a certain meaning, and I would like to import that meaning into a computational algebra. Okay, so I claim that a satisfying answer to this question, what I mean satisfying, an answer where you can say, I understand what extreme or usual means, okay, needs to use a formal probabilistic framework. So I'm pushing an agenda that says, I want you to have a model that describes how these examples of ideals are generated. And then this will help you provide an understanding whether you have an event that is likely or extreme or observed by chance, or, think of it as generic if you would like, okay? So because maybe you're looking for, like I said, an existence of a property. Does my family of ideals happen to have a quadratic Grobner basis for a certain monomial ordering? I mean, you can search through all the monomial orderings or not, but maybe you can prove that it is expected not to have a quadratic Grobner basis or something like this, okay? And so this idea is not entirely new. There is actually a long history on using randomness and using randomness in algebra in general. So this is my explanation of why an algebraist is interested in randomness. Okay, so there's a really old work by Littlewood and Offord on looking at random algebraic equations, where random is defined by taking coefficients of the equation randomly, and then you look at the expected number of real roots. So if you're unfamiliar with this notation, this is, you should you should think of it as average. Okay, so expected value is the average of something that of an event. Okay, so on average, how many real roots do you think you're going to see? All right. If that sounded patronizing, I apologize. I didn't mean it that way. But for those who are not familiar with expectation, I just wanted to offer a different word for it. There's also Schwarz-Zippel lemma, where you look at randomized polynomial time algorithms for testing polynomial identities. So you can use it for a specific application. Is this identity true or not? Or more recently, and I don't have a year, but this is a very recent work, and I'm gonna say last 10 years. It's less than that. It's probably 5. There's a smoothed analysis of algorithms that created a bunch of work in looking at how you. I wanted to start differently this part. If you think of the worst case analysis of algorithms, which is what we usually look at. So, for example, Grosvenor, the Buchberger algorithm is bad because it's doubly exponential in the worst case. The simplex method is bad, but on average it does so well. And so instead of focusing on the worst case analysis, you look at the average case analysis. So what is the expected performance of the algorithm? You look at the worst case and you randomly perturb it a little bit, and you end up having a better overall algorithm. This is called the smoothed analysis of algorithm sense. So randomness enters algebra somehow from different perspectives, and it has done pretty well historically. And so I want to focus on monomial ideals, which ever since I was in grad school seemed too restrictive. Why are you don't know the answer for monomials? But monomial ideals are sufficiently general, as we all know. They capture sort of all the properties that we need to know about in a lot of these applications, because they are Grosvenor degenerations of general ideals. So you can capture a lot of the complexities by just deforming to the monomial ideal. Also, another reason why it's good to look at monomial ideals is you have a strong link to algebraic combinatorics. So you have extra tools that don't live, they're not applicable to general ideals. And the best part today is that monomial ideals generalize graphs. A monomial is just an edge or a hyperedge. It's a list of vertices if you want. So every monomial is a vertex. And then I can just import the probabilistic method, which has been wildly successful in graph theory, to monomial ideal world. Okay, so the goal of this talk and the goal of this work in general is a probabilistic setup for constructing and understanding distributions of monomial ideals and their invariants. And I will describe what I mean by a distribution, and I will describe what I mean by what happens with understanding these distributions. Okay, and what do I mean by invariants? Well, pick your favorite invariants. Today I can mention a little bit about some of the Hilbert function, degree and dimension. Maybe you're looking at regularity, maybe you're looking at other things, okay? So we are importing the probabilistic method from graph theory. Hopefully this is clear. I paused for a second. I have no idea where Q&A is. Everybody's okay? Right. So this credits in this film go to the following collaborators. Don't tell me that Lilith's picture is sideways. It's sideways on her website, so I just copied it, okay? Dane used to be my student, and now he works for the Mitre Corporation. And so Uwe is the outlier in this picture, because the work with him is on a separate paper, but he'll come at the very end. I see a question, or do I? Are we okay? What was I decide?
You're doing great.
Right. So here is the Erdős-Rényi model for random graphs. And for a few slides, it's going to sound like I'm going to talk about graph theory, but no, I just want to explain to you what are these ideas from probabilistic graph theory that we are importing into monomial ideals. Okay. So this is his first probabilistic model for random graphs that I'm sure you're familiar with, even if you don't know it by name. Fix n vertices and choose something called a probability parameter. We're going to call it P. This P is going to be the probability of including each edge independently with that probability. Okay, so I can connect any two of these dots with that probability. So I'm going to consider this pair of nodes, this one, and I'm going to decide whether I'm going to put this edge there or not with probability P. So an example of a graph that you get, when P is 1/16, so is like this. You're going to consider all the possible, pairs and select approximately 1/16 of them, okay? When probability is 1.8, you get more edges in the graph, right? Because every edge has a higher probability of appearing. When you get probability 1/4, this graph becomes denser and denser, right? I'm sorry for the zoom in effect on every slide. I don't know how to fix that. Okay, so this is a probability parameter that governs the model on n vertices where n is fixed, okay? So the question is, what is the role of this parameter? So I'm gonna introduce notation. I'm gonna give name G and P to the distribution on the set of graphs on n vertices with edge probability parameter P. In other words, you have what's a distribution? Well, maybe that's too much, but think of it as a set of graphs, and every graph has a certain probability, and you collect those in a family of functions. Okay, I'm going to use the calligraphic letter G for this distribution. It's a set of on the set of graphs on n vertices. So P is one of the parameters that we get to change if we want. And then just the regular letter capital G is going to be a random variable, the graph random variable that comes with this distribution, okay? And we use a little tilde symbol to explain that that graph was drawn from this distribution. So an example of realization of G is a graph like this, okay? So lowercase g is an observation of this random variable. So it's just so that capital G equals little g is a random event, okay? So when you see capital G, you need to understand that it's a random graph, and then little g is one fixed observation, a realization of it, okay? Question, what is the probability of a fixed graph with e edges? Take your favorite graph and say it has e edges. What's the probability of seeing that graph under this model? Raise hand and then write on the board, right? I mean, if you all had iPads and you were able to tell me, you would probably just tell me. So there were e edges, right? E edges, each edge appeared with probability p independently. So it's p times p times p e times. And then these are the edges. And this here are the non-edges, right? 1 minus p is the probability of not seeing the edge because p is the probability of seeing the edge. And this is how many edges you do not see in the graph, okay? So for a fixed graph, we know the probability of seeing that graph. So that's one type of question we can easily answer once we have a model, right? A different type of question we can easily answer once we have a model is what is the expected degree of a fixed vertex V? Take your favorite person in this network of people and say, how many friends is this person expected to have? How do you answer that question? Oh, well, n minus 1 times p, okay? And the notation for this is again expected degree. So on average, how many neighbors is V gonna have? Meaning the average over all the possible V. So these questions are trivial to answer once you have the formula for the probability and the distribution, right? And so I want to know what's the role of this parameter. I have no idea why I'm drawing this. Okay. What's the role of the parameter P in this graph? You can see that the graph structure depends on P, or seems to, I don't know, maybe. When P is small, you have very few edges. When P is a little bit bigger, your graph looks different. So you can ask questions like this. How does the structure G depend on P? And what happens is you increase the number of vertices. What do I mean by structure of the graph? Well, this is sort of an obvious question. So I'm stealing Lily's computations here. So Lily did a bunch of computations here for from combinatorics. Oops. For example, excuse me. Here we go. So where is my slide? Here we go. She did a bunch of experiments. I decided to take them from her slides because it was easier this way. So there's something that you can make a plot. You can sample a lot of graphs. So for example, when n is 80 vertices and you vary the parameter p from 0 to 0.5, okay, so p is again the probability of seeing an edge, you can compute the probability that that graph is connected. And what you see when p is very small, probability of graph being connected is 0. You have a bunch of, far away edges from each other, and so it's not a connected graph. But as p is large, for example, when p is 0.5 or even 0.3, the probability of the graph being connected is 1. You really expect to see a connected graph. And in fact, what happens is at some point in this region over here, there's a jump, which you may call phase transition or whatever. The graph suddenly almost becomes connected. It never goes disconnected again. Of course, it maybe, but on average, it doesn't, right? So the probability of being connected is basically 1. And so this parameter governs how the structure of the graph changes. And so we say that this is a threshold, right? There's a phase transition, it's called a threshold. I'll come back to this notation in a second, or in a few slides. Okay, so, right. And so I want to write down a formal definition of a threshold function, or not really formal definition, a definition enough where we can move on. Okay, so to understand these phase transitions, I mean, this idea is very old. It goes back to Erdős-Rényi. The point is that many important properties of a graph appear what we call suddenly. So this is the phase transition I mentioned in a previous slide. When probability parameter p is small, almost every random graph doesn't have that property. And when p is large, almost every random graph does have that property. The key is almost, and it's not every, but it's probability one, right? When this happens, and there is a function that separates these two phenomena where property appears and property doesn't appear, that function is called a threshold function for a graph property. And as n grows, as you have more and more vertices, this transition is sharper and sharper. Meaning the graph for the phase transition that I showed starts looking like this, and then like this, and then like this, and then just basically jumps all the way, okay? So another example, it doesn't have to be connectedness. You can say what the property is appearance of a triangle in a graph. It is known that the threshold function for that is 1 over n, meaning when your probability is 1 over n or much less than 1 over n, you're not likely to have a triangle in the graph. When your probability of an edge is much bigger than 1 over n, you are likely almost always to have a triangle in the graph. So you just have too many edges, right? To avoid this property from appearing. Okay. So what can I do? Well, I can do the same thing for monomial ideals. So let me describe the same kind of a model and then demonstrate that this threshold threshold functions exist for monomial ideals and what they can tell us that we didn't know before. So let's define the model first, okay? So I'm gonna fix number of variables equal to 2. This is not to say these are the only results you can write down, but it is the only thing I can draw. Okay, so obviously I don't want to work with 2 variables, monomials in 2 variables, there's nothing going on. But let's say you have n equals 2. It's very possible that on some slides I'm going to have x1 and x2 here instead of x and y. And the whole time I want to think, if you make a model that mimics the model of random graphs, you need to be able to answer those 2 questions that I asked on a couple of slides ago. What is the probability of seeing the ideal that you're seeing? And what is the probability of a certain property happening, right? You need to be able to answer these. Otherwise, this whole model is just a game. So I'm going to fix the number of variables n. I'm going to fix a probability parameter. For this example, let's just do it 1 over 6, okay? Just because I want to have a picture. I'm going to fix a maximum degree. I'm going to call that capital D. In this case, I'm going to make it 6. So my model, which is Erdős-Rényi type, it mimics the random graphs, is going to have 3 parameters. The graphs, it had n and p, and here I have n, p, and d, the maximum degree. Because I need a finite space to sample from. Otherwise, I don't even know how to define anything. Okay. So I'm going to pick monomials randomly in this triangle here. So up to degree 6. I was just kidding. This triangle here, right? I was still kidding. This triangle here, I'm not including the origin. So I'm going to pick monomials in there, pick the black dots from there with probability 1 over 6. So for each dot, with probability 1/6, you include it in the set. And I end up picking these 4 red dots, and this is my set of random monomials in this model. Okay. This is a set of random monomials that defines an ideal, and not every monomial is a minimal generator. So I actually write the corresponding monomial ideal, which is this thing generated by the 3 red corners of this gray staircase, right? So you will see that I'm going to start using x1 up through xn very soon, because we are going to do this for n variables, not 2. And I'm going to call the polynomial ring S. And so picking these dots with a fixed probability, just like I was picking edges in a graph with fixed probability, provides a model for monomial ideals. Am I able to answer silly questions such as, what's the probability of your favorite monomial ideal? So this distribution is going to be called IDNP, in mimicking that in the random graphs we had G was G and P, right? This was a set of all distributions for the graphs on n nodes and P parameter P. I have now distribution I on all ideals that have n variables, maximum degree D, and probability P of picking each monomial to be in the set, yeah? So I'm going to fix any monomial ideal J, and I'm going to write down what's the probability that this random ideal equals my fixed ideal J. So the probability of seeing J that I have picked under this model, it's very cute almost to write down the probability. It's how many corners do you need to generate this ideal? That's how many dots you have, and then 1 minus P are all the dots that are not included, and this is computed using the Hilbert function, because it counts the number of the monomials under the staircase, therefore the number of things that were not included. Similar to number of edges that were not included in the graph, yeah? So this is just literally going down this diagonal and counting the things that are not included in the ideal, okay? If the monomial J is square free, you can interpret this formula using the number of minimal non-faces and faces of the associated simplicial complex. And then you can, you know, make the formula look more complicated, but I mean, it's easy to just write it this way. All right, so otherwise, yeah, okay, so this is it. So yes, we're able to do this. And of course, why am I doing this? Can I make a more general model? This is the easiest model. What else is out there? I mentioned simplicial complexes. Well, there exist models for random simplicial complexes that already generalize graphs, because a complex is another way to generalize a graph. And so I just write down the thing that everybody probably knows, that the set of simplicial complexes on n nodes is in correspondence with the square-free monomial ideals by looking at the non-faces, right? This is your Stanley-Reisner correspondence. Stanley-Reisner correspondence. I don't want to go into all the details there. My only point on this slide is that you can make a most general model for monomial ideals in the universe, which is have every monomial have its own probability. For as many dots you have, that's how many parameters you have. This is ridiculous, it's too many parameters. But that's the most general model, which is useless for us. And then you can take that and specialize it. You can have a graded model where you pick things on every diagonal with fixed probability, or you can make a special correspondence with these probabilities and recover the known models for complexes. And I don't want to write down what the correspondence is, but it's easy. There's something called the Costa-Farber model, where you make a random simplicial complex by recursively going up a dimension and then filling in the simplices, okay? There's linear Meshulam and so on, random clique complexes. We can recover these by starting with the most general random monomial ideal.
Sonja, you have a question.
Yes.
Does the formula on the last slide account for the fact that you can generate the same ideal multiple ways by picking some non-minimal generators? This is from Dylan.
Yes, because, yes, right. So this is, I mean, I'm wiping everything under the rug, but if you go back here, I had this is really a model for random monomials. And then you have to look at the induced monomial ideal. So it is possible that you're gonna end up, you know, with having this and maybe including also these guys. I know I'm outside of the blue line, I'm sorry, but if you had included this and this and this and this would give you the same ideal. So the formula does account for that. We just have to go back and do the counting. Yes. I guess this is why there's something to be proved in the first place. Otherwise, the whole thing will be just counting dots overall. But yeah. Okay. So you can recover all these things. And so what can we really say about ideals? Because my goal is not to go and like reprove things about simplicial complexes. I mean, there's people who do this. I want to see what it is that we can do on the algebra side. And so I have proposed so far, let's just pretend the one model, the Ehrlich type. Let's go back to the one where you have the fixed probability parameter. We can write down the probability of an ideal. Can we write down the probability of seeing a particular Hilbert function? Can you write down the probability of a Krull dimension being a certain number? These are the induced distributions on these invariants. We can write them down using the probabilistic method because we're importing the ideas from graph theory. And then what are the questions that we don't know how to answer yet? Okay, so one of them is this regularity question. Okay, so in the following slides, I will just try to summarize what I think we know. And I say I think because maybe other people prove other stuff in the last few months that I'm not aware. But what we know is the Hilbert function probabilities, Krull dimensions, the first graded and total Betti numbers. So the initial degree and degree complexity, the weak Lefschetz property, which I realized after I made a talk, don't have enough time to define the whole thing, and the projective dimension. And also my question is, what other models are there for monomial ideals and beyond? And I'm working with a couple of people, Dylan Pfeiffer, one of them, and an undergraduate student on these random binomial ideals. There's an obvious model, and then there's an obvious family of extensions to that. So a lot of people have thought about this. And so the question is, can you import more tools to prove the existence of some maybe rare unexpected properties, or debunk that they're rare and prove that they're average? Okay, I mean, I don't know, right? This is where we're going. So a sample result from the paper, and after you see the formula, I realize you don't want me to write the rest of the formulas in the talk, but just to show you what happens, we can prove what's the probability of a Krull dimension being a certain quantity. So we can write down the probability that the coordinate ring has Krull dimension t for every t, okay, as a polynomial. And obviously the polynomial can be pretty. I'm just telling you this is the degree of it. Okay, and I'm just giving you an example. If you're looking at Krull dimension n-1, this is the polynomial. Okay. You can also just sort of say, okay, well, I can't read this. What is it? So we compute a few values. Here's a table of the statistics for 1,000 random monomial ideals sampled on 3 variables, degree up to 10, probability parameter 0.01. That's tiny, right? 1% chance of choosing every monomial. Come on, I got degree up to 10 and I have 3 monomials. If you have high P, you're gonna fill in the diagram and have a trivial ideal pretty soon, right? So you need the parameter to be small in order to generate interesting ideals, okay? And I'll get to that in a second. And so the simulations will, these are the simulations. These are bad titles maybe. This is the sample proportion, and this is the population proportion, okay? So theorem, right? So the values are not that far off, okay? I mean, obviously, all this table says is 1,000 random monomial ideals is large enough to capture the result, okay? But I had a tiny parameter P, right? Because we ran simulations for many, many different values of P and realized that there are ranges of P that provide to you different Krull dimensions. And in fact, this theorem is actually a corollary of several results that we put together, where we actually define threshold functions for Krull dimension. So remember in the graph case, there was a threshold for graph becoming connected. So here there's a threshold for a dimension going from a certain value to the next value. Okay, so this function is e to the t. So my property of a graph used to be graph is connected. Here my property is the dimension is at most t minus 1. And then the corresponding threshold function is e to the minus t. Remember, I wrote down when p is small, then there is no property, or there is a property that happens. And when p is much bigger than t of n, then property p does not happen, does not hold. That was my quote definition of threshold. Well, this is the formal definition, okay? There's a little o and little omega notation. But if you don't like that, just think of it p being much smaller than tn or p being much bigger than t of n, okay? This is the formal definition of a threshold. And so when you put all these together, what happens is for the value of the parameter p being between these two, you're going to get asymptotically, almost surely, a certain Krull dimension, okay? This stands for asymptotically, almost surely. This is the best thing you can get because you're using a probabilistic setup. Where is the asymptotics? Well, you're letting d go to infinity, right? I mean, when you fix your d, you have a finite set of things you're looking for. You can just describe them, right? But the point is, in the graph, the question was what happens when you increase the number of vertices? Can you understand how this property evolves? We're doing a similar thing. We're increasing the degree. We're sliding that we're sliding the blue diagonal on my monomial staircase outward, so we can create more interesting monomial ideals as we go, and then we're figuring out how the Krull dimension changes. So when p is tiny, you get the zero ideal because you like don't pick anything, right? But then when the p is the next tiny range, which is what I had on the example, you have Krull dimension n minus 1, and the larger p cuts down more the staircase, and you get a Krull dimension all the way to 0. Okay, does this make sense? So it's a sequence of results. I'm just putting them all together. So the point is, I can keep going and list a bunch of things. So I'm just going to not explain in too much detail, but I will tell you, you can do a similar thing for first graded Betti number, only the first. It's not easy to talk about all the Betti numbers of an ideal, obviously, but this is a start. If you look at the first Betti number, we have a similar set of thresholds and a similar scenario happens. This is, you guarantee vanishing of the graded Betti number 1j. So this means no generators degree j, right? No minimal generators degree j for a certain range. And so as you increase p, you end up killing or changing the degree, right? Lowering the degree. We can also write down the average total Betti number. So on average number of generators, minimal generators for the ideal, is some formula. So this is a tau divisor function. I chose not to write down the whole thing because it's not intuitive. The point is, one can quantify on average how many Betti numbers or how many minimal generators you expect to see, and you can evaluate this function, and I can show you a table at the end if you're interested, okay? We can also talk about what happens with the degree complexity, which is the telling you the maximum. I just realized that it's 10:34, so I should probably just keep going. So you can describe, you can get some bound on the degree complexity, you can get some average results, and you can get some threshold results just importing the basics from probabilistic graph theory. Okay. The methods we're using are using the first and second moment method and just a definition of what the probability looks like. Okay, so it's nothing too crazy. We can just then simulate the rest of the stuff we're curious about. Are you gonna get a square-free monomial ideal? So this is a lot of simulations where on the horizontal here you have fixed the number of variables. So we have this is four variables, 5, 6, and 7 across the horizontal axis. And then you can vary the degree. So here, this is n equals 7, d equals 9, and you start simulating 1,000 monomials and asking, is it square free? Is it not square free? These are the probabilities of being square free or not. And at some point, you have 7 variables, degree up to 9, and after that, you sort of run into computing troubles. I mean, it takes forever, so we stop. We computed what is the regularity of a random monomial ideal. There clearly seems to be a trend. It clearly seems to depend on both D and N, right? I mean, as you increase D and N, things seem to look differently. I don't have a proof. Is the ideal expected to be Cohen Macaulay? Sometimes no, sometimes maybe. Okay, so on the y-axis of each of these plots is the probability of this, I mean, the frequency of how often you actually see an arithmetically Cohen Macaulay coordinate ring, right? And so there seems to be something going on, but again, I don't have a proof. And then we asked, what's the projective dimension? Because that's, I mean, that's something a lot of us want to know. We noticed a trend and we left this in the paper. We sort of got stuck being able to prove it. But then Jesus, Serkan, Robert, and Lily actually proved it a couple of years after our first paper came out. They proved that projective dimension does have a threshold, okay? And so the reason I really love this result is that it uses the same, model. It has a threshold, and it has, when P is tiny, you have a projective dimension 0 almost surely, and when P is huge, where huge is defined as this, which is not huge at all, right? But okay, much bigger than this tiny. You actually have projective dimension n, okay? And this goes to 1 means almost surely. So almost always, this is what happens. Now, what's the breakthrough in this result? It's just a follow-up, but actually no. What happens is, what we have used is the monotone property of ideals in order to import stuff from random graphs. So this is the secret ingredient in all of the results previous to this slide, is that for random graphs, if you have something called a monotone graph property, then you know there exists a threshold. This is a fact. And so we looked at the Krull dimensions, for example, and we know it's a monotone property. Monotone means, well, you increase the ideal, the dimension always goes in the one direction, and you don't have, sometimes goes up, sometimes go down. You know for certain that it only goes in one direction. Projective dimension doesn't enjoy such a property. It's not monotone, okay? And so you can't just even know that a threshold exists. So they had to go through using some very interesting combinatorial methods to prove that there exists a threshold property. So it doesn't, not all is lost when you can't directly just use the most popular method that there was. Okay, and I really don't want to go over time. So what I'm going to tell you is a super long story. This is an entire paper now in one slide. Okay, so there's something called the weak Lefschetz property that I started to talk with, and then I realized maybe it's not fitting for SAGA. It's a, how should I say this? 1 minute. No, I have a pen, but I choose not to. I'll do this later. Okay, so it's a property of a coordinate ring, okay, where you want it to hold, and it's known to be true in so many cases, but viewed as so special. Okay, and to prove that an algebra has the weak Lefschetz property, often one uses combinatorial methods, and more often than not, you derive it as a consequence of this very special property that the H vector is subject to strict constraints. For example, it has to be unimodal. Okay, so the H vector just counts, the Hilbert function, you write down the series, you look at the coefficients on the top, and those numbers have to go up, maybe stay constant, and then go down. They don't go wiggle up and down. So what you see here is a picture of a bunch of H vectors that are unimodal. These dots are values, and they go up, maybe they stay level, they go down, okay? You don't see something like this. And so if you can prove that the H vector is unimodal, you get the Weak-Lefschetz property for free. And so what we do is, well, we use the random monomials to induce a distribution of random level algebras and compute their expected Hilbert function. So there are several results that one can prove if you just do the right construction, which is the expected H vector is unimodal. So being unimodal is a generic behavior. I don't know, it depends on who you are, how you use the word generic again. We can show that when you have a certain probability for your monomial ideals, then you will have this weak-Lefschetz property with high probability. Okay, so again, I'm not motivating this well because I choose to just sort of show you how it can be used beyond just monomial ideals, which tend to look like toy examples, but they play a huge role in commutative algebra in general. And so I will just end because I think I'm out of time with an advertisement, and thank you for listening of this. I'll stop. I'll take questions.
Thank you, Sonja, for the great talk. So yeah, so for the audience, please post your questions in the Q&A, and you may or not maybe get called on to unmute yourself. I missed a question in the beginning of the talk, but from Fred Hickermill. This person says, you mentioned slight random permutations of worst case conditions. Can you say more what you mean? In continuous problems, we have the concepts of worst case and randomized analysis of errors of algorithms or of the best algorithms for problems. I'm not familiar with slight random permutations. Long question.
So wait, so this was Fred Hickermill? I think yeah. So I think the reason it's taking me a while because I'm trying to put this into your perspective, and it's not trivial.
Hi, Sonja. Yes.
Hi, Fred. I think we should have a conversation.
We can do this offline if it's not of general interest or not easy to answer.
That's no. It is of general interest. My problem is I know where you're coming from, and so I'm having a.
So let me start off with an easier question. Is this Cooker Felipe Cooker or another Cooker?
It is Felipe Cooker.
Okay, so see, I know him from my world, and you know him from your world. So that's
right. Weird. There you go. Okay, so I think so. The way I come. I mean, I don't do smooth analysis of algorithms myself, but it motivates things like this. We know, for example, that if you give me a polynomial ideal in many variables, and you try to compute a Grobner basis, or you try to compute a minimal generating set or something like this, it can be a very complicated problem. And the best we usually say is, well, it's a horrible algorithm. This is the bad runtime. I want to know that what happens on average. And so if you combine the idea of having these varieties defined, or these ideals defined using randomness. So you have, for example, coefficients that I mentioned in another problem. When you slightly perturb the coefficient, you have completely changed your picture. Maybe in your world, maybe you have a function that had spikes, and then you just change one of the coefficients of the function, and that spike just becomes ever so slightly smoothed so that your algorithm doesn't misbehave.
Yeah, I understand what randomized analysis means in my context, but it was your word slight that threw me off, because I had never heard of that.
I'm sorry.
Because we have, in my context, we have worst case and we have randomized or average case. We have actually a couple of different concepts.
I omit the word slight.
Okay, then I think I know what.
Sorry. Yeah, I'm sorry.
No problem. Thank you.
Sorry.
I had a question, Sonja.
Mm-hmm. So
you're pulling from many different sources, and I know there's some graduate students in the audience. If somebody was interested in getting started in this type of research area, what would you recommend for some of the first things that they look at to read, or papers or textbooks?
Right. So I mean, I do realize that I didn't actually give references because I don't know how to do it properly. But if you go back and look at the two names, specifically if you're asking about where graduate students should get started, this is the thing to notice. The random monomial ideals paper, the one that we published in 2017, included Lily and Dane, both of whom were students at the time. So their theses contain wonderful chapters. In particular, Dane's contribution has to do with, oh, well, I forget now which one is which. One had the dimension and one had the Betti numbers. I think the Betti numbers go here and the Krull dimension is in this one. But anyway, they both explain how the probabilistic method is used. And so they'll give you references for the random graph literature, for the randomness in algebra literature, and obviously for some of the monomial ideal stuff that it comes from. So instead of just saying, go read the paper from 2017, I think these theses online have more thorough chapters that will guide you through the references better.
Thank you. So we're at 10:45, but after we thank Sonja in a second again, please stick around for our post-discussion that will not be recorded if you want to catch up and see each other. So with that, let's thank Sonja again.
Thank you.